Hey guys, in this video we are going to be talking about enthalpy of chemical reactions. So up until now we have been kind of talking about energy movement, energy transfer, etc. in terms of endo-exothermic reactions. We've identified a little bit of kind of calculating how that energy transfers, how much energy transfers, how different objects transfer energy differently. And now we're going to dive a little bit into kind of the final part of thermochemistry, which is how chemical reactions differ slightly from physical processes in terms of energy movement. Alright, so as mentioned, physical processes such as phase changes or an object just kind of gaining energy from another object through conduction or convection or radiation or whatever it may be. But those types of situations, when we look at those and we calculate or determine the delta H, what we're really determining is how much energy really just transferred from one location to another. How much energy left the object, was absorbed by the object, or anything related to that. We're just looking for energy movement. But in chemical reactions, we have to remember that the energy we're referring to is, in a lot of cases, heat energy, but it's also things like gravitational energy. It's also things like magnetic energy, etc., where it's really talking about holding the particles together. So in a chemical reaction, delta H is the result of differences between the energy being released and absorbed from bonds. All right? So we remember that we have objects such as, well, let's just go with our old faithful over here, water. All right, so water right now is in what we consider essentially a low energetic state. When something is bonded, it means that it is at a lower energy state than it was previously, traditionally, and it means that it is stable, comfortable. It's a happy place for that particular atom or molecule. Perhaps. At least it's a low energetic state. Okay, so when you are breaking bonds, you have to actually add energy to them to get them to break. And think about the gas theory, the kinetic molecular theory, where we said that the more energy something has, the faster the particles move. Well, these particles right now, the two H's and the O, are connected, so they're really not moving away from each other at all. Or hardly at all. So we have to add energy to get them to actually agree to separate. So I have to actually put energy in to get them to separate from one another. Now, if I want the bond to actually form, what I want to realize is that there's a couple things going on here. We have, that's good enough. So we have the atom, and these particles are moving around pretty rapidly. So I'm just going to kind of draw arrows to show, they're doing their thing. They're kind of trucking around, if you will. And so they have a pretty decent amount of energy. Now, when they come together to form their bond, they're going to have to release some of that energy to actually connect together and get to that low energetic state. So you can't have two particles with extremely high energy rapidly trying to move in opposite directions actually bond. So those two things have to release that energy in order to form that bond. So the difference between the bond breaking and the bond making is your delta H. Sometimes it's going to be in here somewhere, meaning it's not, or it's a negative delta H. Sometimes it's going to, or excuse me, a positive delta H. Sometimes it's going to be more like this, where the energy is released and we would see a negative delta H from the reaction itself. So the reaction is losing energy as the bonds are formed. So like we just said, when we go to break a bond, it's endothermic because the energy has to go in to actually make the particles move away from each other. When you form bonds, it's exothermic because they're already moving pretty energetically. They have to release that energy to come together. And down here at the bottom, you'll see average bond enthalpies. Now take a note real quick that this is kilojoules per mole, because remember, when we're looking at these, it's difficult for us to say, oh, 413 kilojoules were released. Well, that means one carbon-hydrogen bond was formed. Well, no, not really. So we remember that we measure most things in moles in chemistry, or when we're looking at things, we're measuring it per mole. And that's what this is. This is saying, okay, well, if I have a mole of carbon and a mole of hydrogen, and I'm making a mole of carbon-hydrogen bonds, I release 413 kilojoules. Otherwise, it's such a small value that it's difficult to measure just one bond forming. So what you'll notice is that every bond has different things. Even a carbon-carbon bond that's single versus a carbon-carbon bond that's double or triple is going to be vastly different. So every single bond produces or requires different quantities of energy to either break or make the bond. So as mentioned, the difference between the energy required to break bonds and the energy released when bonds form is our delta H reaction. If it comes out negative, that means the reaction's exothermic, meaning the products are at a lower energetic state than the reactants, so it required energy to break the bonds and then release them as they formed, and at the end, it released more than it took in to break the bonds or to bring the particles together, or whatever the case is, right? On the endothermic side, the products are higher, the delta H is positive, because the particles in that case required more energy to actually perhaps break the bonds than the bonds that were reformed afterwards once the particles came together. So again, we're not just really picturing, when we're picturing these graphs, we shouldn't be thinking about like one carbon and one hydrogen coming together. We should be realizing that, you know, those carbons are going to come in maybe in the form of CO2, and the hydrogens maybe are coming in methane, CH4. And so those things have to break to release the atoms to actually then reform. A lot of atoms, as we know, basic gaseous atoms especially, are diatomic. So they're always going to be bonded with another one of themselves, and so they have to break that bond prior to forming a new one. So we kind of, throughout the year, we always just talked about, oh yeah, bonds form, blah, blah, blah. We didn't always say exactly that, okay, well, in order for those bonds to form, those atoms had to come from somewhere, and it is extremely rare that those atoms were just randomly floating by themselves and happened to get near each other. Now, we've said that when we overall end up with a positive delta H of a reaction, that means the reaction throughout all of its processes ends up at a higher energy state for its products than it started with in its reactants. And so that means that the actual energy is going into the reaction, or more energy is actually going into the reaction than is coming out. And so the delta H is written going into the reaction. So if we have a thermochemical equation, a fancy way of saying, well, we just take a chemical equation and add in the energy. That's all we're saying by saying thermochemical equation. So we took the exact same reaction here, magnesium oxide decomposing into oxygen and magnesium, and then we just said, oh, okay, well, by the way, it requires 1203.2 kilojoules to make those 2 moles of MgO actually break down. Interesting to note that it is referring to 2 moles of MgO, not just 1. That will make a difference at some point. On the exothermic side, if a delta H reaction is negative, that means that when the bonds formed to make the new products, we ended up releasing more energy than we actually put into the reaction to break the original bonds. So it comes out negative. We write that on the product side. So notice it says plus 572 kilojoules. And you may say, well, why doesn't it say plus negative 572 kilojoules? Well, if you say plus negative, isn't that just minus or plus math? Anyways, so the reason it's that is because it's on the product side. So we know that it's something that's coming out of the reaction. So we don't need a sign on it, because if we said negative 572 energy came out, that doesn't make sense. That's like saying, oh, okay, well, you know, I was standing outside Target and negative 10 people walked out. Does that mean 10 people walked in? Or do you just not know how to count? I don't know. So we're not going to do an extensive amount of work with this, although admittedly this is something that we had to kind of cut down this year. So going into APIB chemistry, it won't be a prerequisite required piece of information, but it may be something that's skimmed over pretty quickly to get into the actual activity of it, so I did want to hit on it right now, okay? So every substance that's formed requires a certain amount of energy. So we just saw that, let's say, you know, we have a carbon-hydrogen bond, and it was, I don't remember, 4 something kilojoules per whatever, okay? So for each carbon-hydrogen bond, I would need 400 and something kilojoules to actually, or is released when it forms, or whatever the case is, okay? Now, let's say we are creating the compound methane. Boop, boop, boop. Oh, okay, all right, I just clicked on something I wasn't supposed, well, I can't fit it up there, but you get the idea. All right, okay. So let's say we're building methane. Well, that is the most hideous methane I've ever drawn, but you guys hopefully can get the idea. CH4, a carbon with 4 hydrogens on the 4 poles. There we go. So if each carbon-hydrogen bond is 400 blah, 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 then we would actually say, okay, well then the whole molecule of methane takes 4 times that, or releases 4 times that when it forms, or whatever it is, okay? And so the overall molecule, CH4, has a delta H formation that it requires to actually just form that molecule. Now, the reaction as a whole, maybe those carbon and hydrogens are coming in by themselves, in which case there's not going to be a lot of energy having to go in to actually break any bonds or anything like that. We're just forming bonds. But perhaps it's also coming in as H2O and CO2, in which case those bonds have to be broken, etc. So the delta H of the reaction is affected by the amount of energy it actually takes to build and break down each individual part of the reaction itself. You add all of that together, and that's what you get. So the equation that, like I said, we're not going to use in calculations necessarily this semester, although I will post an optional activity if you are interested in doing it, just to kind of say, you know what, I don't feel like it'd be that hard. I want to try and see if I can do it, and I'm bored. I will post that. It is not required, but it is optional if you'd like to attempt that, especially if you know you have signed up for AP or IB chemistry. You really should be taking that optional assignment, okay? So delta H of the overall reaction is calculated by looking at the delta H of formation of the products minus delta H of formation of the reactants, okay? Now, if we think about that, essentially we're saying final minus initial, okay? So final energy minus initial energy, and that gives us our delta energy, okay? So the delta H of formation of the products, those are given standard values. So there is a chart that actually says, for CO2, this is the delta H formation. For H2O, this is the delta H formation every time, okay? Or under standard conditions at least. So those are set values, and so essentially when you are calculating delta H of reaction, you just say, okay, well, how much energy is actually released when I form the products? How much energy is required to break down the reactants? I subtract that, boom, I have my answer. Now, going back to something I touched on earlier, the question up here that's kind of guiding this particular slide is saying, how is the delta H reaction affected by the amount of substance? So it says, you may have noticed that the table of bond enthalpies is given in kilojoules per mole. So when we say that it takes, and this is true also for the delta H's formation, if we say, okay, it takes this much energy to make CH4, we're not saying one CH4, we're saying a mole of CH4, okay? And so if we had 2 moles of CH4, well, then it would take twice as much. It's kind of like, to me, I think of it as like paint, okay? If we say, oh, it takes 1 can of paint to paint this room, okay, well, I need to paint 2 rooms that size. Okay, well, then I guess you need 2 cans of paint, right? So, hi, baby. Sorry, my cat walked in and can't ignore her. So the idea there being that if the delta H reaction for the formation of CO2 is negative 200 kilojoules, then if we doubled the reaction, then it would be negative 400 kilojoules. So it's essentially just saying, okay, this is what you need. It's almost like a cost of the item, you know? So if the item is $2.99 and you need 2 of them, oh no, I don't want to do that. If the item is $3 and you need 2 of them, they're not going to change price necessarily. Now, I know some of you are like, well, sometimes they're 2 for $5. Well, sure, but that's not how chemistry works. We don't have 2 for $5 sales in chemistry. So, you know, you have to kind of just say, okay, well, then if I need to double the recipe, then I need to double the product. All right, so again, I'd like for you to complete the basic required activities for this week, and then if you'd like to do the optionals, do those as well.